All right. Thank you very much for the introduction. I understood everything, but sounded good. Okay. So this is probably a strange question, right? You are running Postgres. I guess you know what you're running. And actually, I'm going to try to claim today that maybe you don't know what you're running. It might sound a little bit stupid, but may have very deep implications. So let me start with kind of a small joke or a meme to introduce the topic, right? You probably know this famous meme from the internet, right? And let's apply to the topic. So you know what Postgres are you running, right? Yes, sure. But actually, do you know who built the package you're using and how it was built? Actually, you may even think you know, but most likely you don't. So, to try to explain where I'm trying to get at, let's run a small experiment. Here's the set of commands, right, to unpack a binary from a package, right? In this case, I'm trying here to download a Debian package from the so-called official apt repository from Postgres, right? At version Postgres 17.0-1, right? This is important because I want to keep this version constant. Here's a set of commands. They're not really relevant, but basically I run these commands to extract the binary from the official, again, apt, so deb package, the official one, and compute the SHA-256 of the package, which is essentially a digest. This returns a number that starts with 108. That's enough for us to remember, right? So extract the binary, run a digest, and get a number. Now let's repeat the same operation for the very same version, 17.0-1, right? Against the official RPM package. I need to run this set of commands. Again, the very same Postgres version, also the official package, in this case from the RPM or YAM repository. And when I run the digest, I don't know if you can see it from the back, but I get a number that starts with 860. That is not the same number I got before. It started with 108, which means that the binary is not the same. So I'm getting a different binary. Well, I mean, kind of makes sense because one is Red Hat, the other one is RPM, the other one is Debian. All right, let's try this again by basically pulling the official Docker image from Postgres, which is based on apt, on that package. I should get the same as the first one at least, right? By the way, it's interesting that the official Debian package, the official Postgres Docker image, is built by Docker, not by the Postgres project. It's official from Docker's official's perspective. That's something not everybody knows. But anyway, so I run the equivalent commands to extract the binary from the Docker official image at the very same version 17.0.1 that is based on the apt parameters, the Debian package. And if I run this, I get now a number that starts by 852, which is again different. So I've run this simple experiment. Here's a summary. And for every version of Postgres that I tried, I'm getting a different binary. Well, we may argue this is kind of different environments, but at the end of the day, I guess you're trying to see, you're probably seeing where I'm trying to get at. If I want to know which Postgres I'm running, well, there's different Postgreses, at least different binaries, for the very same version from official sources. This problem gets worse. Even the source code is different. What? I mean, the binaries come from source, right? And which one is the real source for Postgres? Well, let's download from the official site for Postgres source code, right? And in this case, there's no binary, so I cannot run a digest on the binary, but I cannot run a digest on the equivalent tar file from the source code, right? Here I get this number, BF8, okay? But Postgres is developed on a Git repository. And Git has a command to generate an archive file. So let's go to the Git repository and get an archive file. I do that. I clone the official Git repository. I generate an archive file on the particular version we're looking at. And I get another number, 4FD, which is also different from the running the same command on the tar file from the download side of Postgres. So not even the source seems to be the same. Actually, this is a known problem. Is explained very well on the blog posted at the bottom of this screen, this slide. And in reality, in this case, it's just a different, it's an effect caused by using different versions of the tar command. Reality, the source is the same. But it creates confusion, doesn't it? The binaries are not the same. The source code seems not to be the same. So there's a problem here. Now, with this introduction, let me please allow to introduce myself. This was the intro. This is like the movies, right? First there's a little bit of a teaser, then the intro, and then the rest of the topic. So I'm trying to follow this. I founded a company called Postgres, which means on Postgres. And I basically spend my time doing R&D, research and development, which is a nice way I'm saying I'm doing stupid things. Now, some of those stupid things end up being interesting. For example, we built a platform for running Postgres on Kubernetes called StackGres, or some other projects that come to light. But most of the time, I like to also speak about. I come to conference like this one. Thank you for the invitation. If you're interested, I have more than 140 talks on my personal website, which is that one down there. Most of them are recorded with the slides, with everything. This one will also be uploaded there after the fact. So, let's go back to the topic. Imagine that we want to analyze how a Postgres distribution should in reality be built, and what are the challenges in doing so. Let's start with a small conversation, back to the original topic. Let's imagine this is a dialogue. I don't have a co-speaker, so I cannot do this with another person, but you can imagine the dialogue like, okay, so you're using open source, right? Yeah, I'm using open source. And why are you using open source? Oh, because if I run some system, I can always go back to the source code and know what it's doing, inspect it, analyze, right? This is the theory. But in reality, do we know the binary we are running, where it came from? Is anyone here capable of ensuring that the binaries you're running in production have been built in a way or in a system so isolated that has not been tainted by any potential malware? Because I'm not talking about some theoretical exercise. I'm talking about reality. I guess you're well aware of this famous or infamous vulnerability that was explained recently, appeared some months ago, called the XC vulnerability. It was actually discovered by, it's not a Postgres vulnerability, but it was discovered actually by a Postgres hacker, by Andres. This is a vulnerability, not in Postgres, but in a library called XC that is used by SSH, which could also be used by Postgres directly or indirectly. But if you happen to use Postgres or any other software that depends on XC, you could be running a backdoor to where all the users could connect and control your systems. So how do you know today that the Postgres version that you're running is not linked against the vulnerable version of XC? It's not easy. So to try to prevent this kind of problems where we really don't know our environment, how it's been built, and if it's safe enough or not, there is a set of theory and practice behind building systems, which is called reproducible builds. Reproducible builds, it's a technology and a set of, again, best practices to create or to build software in a way that is reproducible. There's a lot of information on this website. I encourage you to check it out. So what it means that something is built in a reproducible manner? Well, let's actually say that if you have a binary and you compare it byte by byte, it has to be the same. If I build a software twice, potentially on different environments, as I did at the beginning of the exercise, if I build it at different times on time, potentially in different, if I build it on different architectures, for example, I would still get the same binary byte by byte. This is easy to compare by running a digest, as I was doing at the beginning of my presentation. Of course, there's always some small details here. The devil is in the details, as I may say, like, okay, so maybe two binaries are essentially the same, except for some metadata, which I don't care about. But in practice, I would prefer to say, oh, yes, just give me the same binary. And believe it or not, despite compilers being, they can provide the same output given the same input. That's very obvious. They're not compiling using AI, at least not yet, I guess. They're deterministic, therefore, you can get very easily different binaries by compiling in different ways or different environments. So, why is it important to have a reproducible build? Well, a reproducible build is important because I want to know exactly what I'm running, right? This means that, if, for example, if I have a performance problem, I want to set up a test environment to troubleshoot my problem. I really want to have the same environment. If I set up a test environment and it happens to be different, then how will I ensure I'm fixing or properly troubleshooting my issue? All the movement behind reproducible builds started are very large companies like Facebook and Google. Have been the two that have done the most work in these regards. Do you imagine running a fleet of 1 million servers like they do? And having to create an inventory of the different versions of the binaries you have deployed across many millions of servers? No. You want to have the very same version everywhere, right? So if you want to have a consistent environment, you really want to have the same version everywhere. And last but not least, if you need to distribute binaries across 1 million servers, caching is going to help a lot if they are reproducible, if they are the same binaries. If you have different, slightly different versions each time, then you're not going to use any caching effects, right? So, let's dive even more into this topic. Let's talk about hermeticity. Because you're thinking, oh, reproducible builds, this seems quite obvious, right? If I compile things, I'll get the same results. The reality is that most often, you will not get the same results. Because almost every build system out there will be tainted by the environment on which it is built. Basically, if I build something on my laptop and you build the same thing on your laptop, we will most likely get different results. It will not be reproducible. And why is that? Most of the time, it's because the environment on which we are building this software is not hermetic. What I have on my system is influencing the build. And that's why if I have a vulnerable XC version and you have on your laptop a non-vulnerable XC version, we'll get different binaries, and one will be tainted, the other one will not. So to prevent from this, I want to build software, and everybody who builds software should build in this way, in a hermetic manner. A hermetic system is one that is immune to the environment. To do this, essentially, a hermetic build system will create kind of a container. Doesn't need to be a Linux container per se, but imagine a container sometimes called a sandbox, which is empty. And then you bring in explicitly controlled versions of all the software you need to build, and even the compilers and even the Linux system itself into that sandbox. Therefore, it's reproducible because it will run the same way on any computer. Right? If you want to go further, there's here definitions of hermeticity. So, why it's important to be hermetic and where it leads to, right? So if you have a hermetic system, you can achieve reproducibility. That's not guarantee, it's not enough, but it's a way to achieve reproducibility, which I already discussed is a desirable property. It will obviously protect from poisoning from the environment, contamination from your own environment. Right? You'll produce clean builds anywhere. And it also allows the ability to run self-contained binaries, or binaries that do not depend on the environment. This is actually not possible for Postgres of today. We cannot compile Postgres statically, which is a shame. But it will be great, because in this case, it doesn't depend on an external library, and therefore, you know exactly what you're getting. You do not depend on the environment. So, other than the environment, which is obviously a way of producing different binaries, which other causes may trigger that a build is not reproducible? Well, there's a whole set of problems. And we've been working on some of them, and we found that Postgres has a few of them. So Postgres, as of today, as it is, it's actually not building in a reproducible manner for most of the cases. Sometimes there's timestamps embedded in the binary. Obviously, if it's a timestamp of when compilation happened, the binary will change over time. There is the R path, or the relative path functionality of ELF files, which encoded or hardcodes paths into the binary. Obviously, that will depend on the environment. There is similarly the back information that is sometimes stored into the binary, which is obviously may depend on your environment and may lead to different binaries. There is strings embedded. Postgres tends to store a few strings on the binary that reflect the build system. So if you build in a different system, it will also cause differences, right? When you compile Postgres, there are stages of code generation, and this code generation emits also information that gets encoded into the binary, so different versions will lead to different binaries. So there's a lot of reasons where software will not be reproducible, so it's a lot of effort to build Postgres in a way that is reproducible and hermetic, but it would bring a huge set of advantages to achieve something like this. But you'll think, oh, but actually Postgres is reproducible. I mean, Postgres packages, for example, in the case of deb packages, they are built from Debian packages, and Debian packages are reproducible. Most of them are, but Postgres is among those. And yes, but no. So they are reproducible if you have a fixed, predefined, and build path environment. So it's kind of yes and no. If you build it only on these very particular conditions, on these very particular systems, with these very particular libraries, and you need to set up and construct that build environment, and I promise you I've tried, it's not easy, then you will get the same binaries over and over. But if you want to kind of reproduce this easily way yourself, you will not. This is more easily understandable if we look at how Postgres source package is actually packaged. Just the source code, not even built. To produce the release artifact for the Postgres source code, you need to have access to a specific server from the Postgres project that only very few people have access to. This sounds a bit contradictory with open source, right? The source is open to anyone, yet to produce a valid Postgres source package, only 3 people in the world can do it as of today. Why can't I produce a valid equivalent bit by bit, byte by byte source package for Postgres? Well, I cannot, because software is packaged in a system which is non-hermetic. If we were able to build Postgres in a hermetic way, anyone could produce a software package for Postgres exactly byte by byte the same. Now, we can go very deep on this topic. Further down the road of reproducible builds, there's this theory we call bootstrappable builds, which is basically how do you want to build, you want to create, I don't know if that's the same word, yogurt, right? Yogurt that you eat in the breakfast. So how do you create yogurt? Well, take yogurt and add some ingredients, and you'll, okay, but where do I get that yogurt? It's a bit of a chicken and egg problem. Same happens with compilers. Okay, how do I compile Postgres? With a compiler. Where do I get the compiler? Well, I compile it with a compiler. Okay, and who compiles that compiler? That compiles the compiler, right? And if you trace this back, there's a whole theory behind this called bootstrappable builds that enables a path to achieve a system that compiles everything from a tiny, tiny piece of software that you can inspect and you can trust. The idea is that to prevent malware being injected into build process or artifacts, or essentially achieving non-reproducible builds, systems like GUIs will actually achieve for pure bootstrappability, do this and start from a tiny piece of software. It's something you trust. It's always something you need to trust, but it's tiny. With this, you compile a small compiler. It's not even a C compiler yet. With this compiler, you compile another compiler. This compiler is a tiny C compiler. With this tiny C compiler, you compile another thing. You compile make, you compile configure, auto tools, whatever. Then you compile a GCC 2.95 ancient version. And with this compiler, you can compile all the compiler. And at the end of the day, you get all the tools that you need to build something like Postgres. But you can trust the whole chain is totally verified and totally hermetic. Doesn't depend on the environment. Well, this is kind of a dream. It's on the way. So, can we apply all these principles? Can we achieve a system that will lead to reproducibility and hermeticity to Postgres distributions? This is the questions we asked ourselves sometime, and we strive to answer, and we've been working hard on achieving this. So, what can we apply for a Postgres distribution to make it truly, truly secure? Well, first of all, we would like to have SBOMs. The SBOM, or software bill of materials, is similar to the bill of materials document that is used in construction. If you're building a machine, let's say kind of a plane, right? You need a list of parts to build the plane, right? It's typically a Excel spreadsheet. You need this number of bolts of this type, you need these metal planes, you need whatever, right? So this list of all the components that you use to build something is called a bill of materials. Well, a software bill of materials is pretty much the same. It's all the software libraries and versions and components and provenance, this package of software, where did it come from? At which particular version? What is the repo? What is the digest of this package? On which dependencies has this particular package? So it's a document that stores all this information so you can understand, you can trace it back, you can see if Postgres was built against XC 5.4, which is the one that was vulnerable, right? Just by looking at the SBOM. And SBOMs are becoming more and more important. A lot of people are starting to demand SBOMs. Please provide your package and provide an SBOM with it. Demonstrate how you have built this software, because I want to know if this package may be vulnerable. So much that the White House emitted an order in 2021 that said that SBOMs are a recommended practice and will become mandatory for any contract with the US government within the next years. And most likely, a significant part of the world will follow after this and start requiring SBOMs. This is, well, probably cannot see very well, but this is an example of an SBOM. This is, at the end of the day, it's just a JSON document listing all the dependencies and the versions and whatnot. There's a couple of standards about SBOM documents. Well, even better than having just an SBOM is having a verifiable SBOM. What if I get a binary, I get an SBOM, and the SBOM is fake? The SBOM is saying, yeah, you have this dependency, everything looks good, but it's not the reality. There's still a malware somewhere on the binary. So if I have a system that is fully reproducible and is fully hermetic, I can rerun the command that generates the SBOM and validate that the SBOM is truthful. So an SBOM by itself will not take me very far. unless I can trust that SBOM. But the best way of trusting it is regenerating it and ensuring that I get exactly the same thing. But again, for that, I need a reproducible hermetic environment. If I'm distributing software as container images, again, my purpose here is to further increase security. I could also I can digitally sign the container images. I can also digitally sign packages. But the ecosystem around container images is becoming a very convenient way to distribute software, because it allows you to distribute the images and use existing tooling to sign and verify signatures, which makes it very convenient. And it's obvious the benefits that it provides, signing images. Also, if we continue with this paradigm of packing as container images, there's tooling to also analyze for automatic security vulnerabilities. It is interesting that most of the security tools that look for vulnerabilities in software do so by looking at the fingerprints of the packages that you have installed. But they work much better, and they're starting to work like this, if you provide an SBOM. Because they can then definitely just look into the SBOM, if the SBOM is trustable, obviously, and then look at the libraries and dependencies that you have used there, and then tell you if that particular version of a given dependency that you use to compile your package is vulnerable or not. So, a lot of topics right here. Can we bring them all together in one place? Can we build a distribution, a Postgres distribution, that somehow follows all or most of these principles? Well, I believe the answer is yes. And that's what I wanted to somehow introduce today, a project that we call Monogress. So Monogress is a Postgres monorepo. I don't know if you're familiar with the concept of monorepos. It's, by the way, a concept that I didn't like some time ago. To be truthful, I didn't understand what it really meant. But when I studied the concept, I started to understand how important it is. A monorepo is a single repo. Sounds simple. You put everything there. Looks like, why do you want to put everything into one repository, and why is that relevant? I like modularity. Normally, I would split different projects in different repos. But the goal of a monorepo is not to make things more complicated or more bloated, but rather to create a coherent environment for building software. To make sure that all software that I build, for example, uses the same libraries, links against the same libraries, uses the same build system, that I can build it all at once. So Monogress is a monorepo because we want to build the whole Postgres ecosystem, mostly Postgres, derivatives, and all their extensions in a single place. So the idea is to build, as I'm saying, a centralized repository when Postgres and all the extensions are there somehow and can be built from source in a reproducible and hermetic manner, obviously. So, main goals of this project is to provide Postgres to be built in a fully hermetic and reproducible way. It's going to be, it's not yet public at least, but it's going to be a fully open source repository under the Apache 2 license. And the goal is this not to be an end product, but rather to be an upstream distribution. A distribution where others could create a derived version and create their own packaging. Actually, the goal of Monogress is not to even produce any output or any direct output. The idea is to provide Postgres source, extension source, derivative versions source, and all the build scripts necessary to build everything in a fully hermetic and reproducible manner. Because we believe so much in how important this is to build Postgres and its ecosystem, we want to bring everything to a single place, to a central place, and allow anyone to derive packages from this project. But with the assurance that everything that you build based on this project will be, again, reproducible and hermetic. So that instead of requiring a golden server, instead of requiring this server where only 3 people in the world can build the software and achieve the same result, that any of us could take our laptop or our build servers or our CI environment or whatever we want and get to the same binary, byte by byte, with an SBOM. And we can trace back the software to the very beginning of how it was built and against which libraries it was built. How do we do this? Well, by using build tools that are specialized for reproducible builds. There are several of them. The most important and well-known is called Bazel. Bazel is a tool that was open sourced by Google some 10 years ago, built from an internal system that they use at Google, built exactly with these principles in mind. Google has been one of the most active participants in reproducible builds. They need this for building software for millions of servers, and they want them obviously to be fully reproducible. So it's an interesting system that claims that out of fast and correctness, you can choose both. Unlike most computer science, or you have to make a trade-off. Apparently, there's no trade-offs here. Actually, I would say there is a trade-off. And the trade-off is that Bazel is a bit hard to use and to learn. But it's a great build software. And we have written already tons of Bazel code to allow building Postgres and extensions in a reproducible, hermetic way. So, what is going to be the next steps? Well, first of all, we want to publish this repository as open source. This is going to happen this year in a few weeks or months. Stage 1 of the project is almost complete as we speak. We're also writing, we've built a lot of automation into, well, actually Bazel is a very complete build system. And we have already built the technology that adding, for example, a new extension to Postgres could be just a few lines of Bazel code. Bazel code, by the way, the syntax, it uses a syntax very similar to Python. It's written in a language called Starlark, which is a subset of Python. So if you're familiar with Python, it's trivial. If you're not familiar with Python, it looks like structs or objects, just pass properties. And building an extension is as simple as specifying the URL of the repo, the tags you want to filter out or select, and a few others. But we want to go further than this. So right now, the way Postgres builds the software is by encoding the properties of every extension, for example, in a JSON file that you populate for every version. You provide the digest of the source code of every version. But this involves a little bit of manual effort. So as part of the project, we're also building a software called Monobot, which is kind of a crawler that goes to the repositories of the extensions, extracts all the versions, computes the hash of all the packages, source packages, and creates this JSON file so that builds will be fully automated. So any new extension will publish a new version, will be compiled automatically by the software. Right now, we have support for a few extensions, but we want to add support for hundreds of extensions, following the lead by the great Pigsty project, right? And well, the idea is to also support multiple Postgres variants of or forks like Babelfish or IvorySQL, for example. And one of the advantages, by the way, for these Postgres forks is that because of the build system is fully automated, we can compile them and verify them against every extension that the system will support. So we'll be able to provide feedback about which extensions, for example, would not work with Ivory, right? To mention some example. And that's pretty much it. I hope we have some time for questions, if you have any. Thank you.
Thank you for this nice introduction to these reproducible builds. I was wondering what drives you to use Babel or Bazel instead of Geeks or Nix or alternative Nixflex. Superbase is using Nixflex to do the same thing, more or less, and I wonder.
Well, that's an excellent question. There's a few systems that ensure or allow you to ensure or create reproducible environments. Bazel is one of them, the one that we chose. Nix also allows this, follows this philosophy very strictly. And there's others, as I mentioned. We actually did a little bit of research on Nix as an option. And first of all, I am totally in love with Nix philosophy. And I'm running Nix on my computer, and I'm using a lot of stuff based on Nix. I think it's a great system. Nix syntax or Nix configuration language. I could use some adjectives to qualify it, but since this is being recorded, I'm going to be prudent and not mention them. But the main reason for not using Nix is not this one. It's that Nix's philosophy is closer to a packaging system than a build system. Even though it could do both, and actually has the advantage that it has Nix packages, and it makes very easy to bring software dependencies. The reality is that there's two main problems with Nix that we identified. One of them is that it's a little bit more coarse-grained than Bazel. In Bazel, we can cherry pick and go very fine-grained and exactly specify how we want things or which components of the things we want to build. Something that in Nix is technically possible, but it takes so much more effort. The second thing is that Nix has a very particular philosophy. And if we're building software, for example, where files are placed, right? And if we're building software for Postgres, where people tend to expect things to be placed on given directories, on work in a given way, creating packages meant for general use, where binaries will end up being laid out in a totally different paths, might be too awkward. There's also ways in Nix of fixing that and generating layouts similar to FHS, but it also meant a lot of work. So in summary, we researched a lot, we considered Nix deeply, love for Nix, no problem there, but we found Bazel a more proper answer as easy it is a pure build system and allows to have complete control over the whole process.
So I have a little experience with Bazel. So if I run Bazel from my laptop, so it will download some Bazel plugin from internet, but it still depends on my local compiler, GCC or the mic CLAN to compile the code, right? So if I run Bazel on my laptop and you run on your laptop, how the two builds can get the exact same bytes, right? So I know Bazel has some caching mechanism. So it's your idea is like you build a central cache that ensure all the builds to generate the same bytes.
Yeah, that is an excellent question. So I can dive deeper a little bit on how Bazel works. The answer to your question is that Bazel promotes itself as a reproducible hermetic build system. The reality is that by default it is not. And that looks like your experience. You need to configure Bazel to do that. But by default, it will take the compiler on your system. That is the wrong thing to do. How we're going to generate the same binary if you have a different compiler than mine? Most likely they will produce different output. So we are dealing with this problem. Bazel has the option. Bazel basically, when it's compiling a project, it will generate a tree of all the steps it needs to do to produce a compilation, right? For each node of that tree, it's going to use a sandbox. A sandbox can be something very lenient, very permeable to the system, which is the default, or you can create a very strict sandbox that will only exist for that particular node of the compilation process and will only include the software you tell it to include. Using this sandbox in a strict manner is very hard because the strictest sandbox is empty and you cannot run anything on it. It's not that you have a compiler, you don't have libc, you don't have ls, you don't have cp to even copy the results of the binary, right? But it's possible to start from a, let's say, simple sandbox and then bring everything in explicitly at explicit versions and explicit hashes. For example, the compiler, this can be done by using a concept of Bazel called toolchains. And there are hermetic and reproducible toolchains available in the Bazel ecosystem. So no, we're not using a big centralized cache. You can start from zero from your computer. It will definitely download stuff, but this is stuff that will download is noted on config files at a particular hash, a particular version, a particular repository, and will always be the same for you and for me. So it achieves this reproducibility based on these concepts. There's things that are not perfect, and there's people working on improving the state of the art. The base sandbox minimal image with the minimal components on it doesn't exist. There's people working on a reproducible sandbox. For now, we are achieving this by using a small container image because it's immutable, and also you can pin it on a hash. Right now, the process of creating this container image is not fully reproducible by itself in this very small image, but we will also do. Generate also with Bazel. Bazel can also generate container images. But most of the components used are pulled from the outside at very specific versions and ensuring every environment will be the same. By the way, if you have experience with Bazel, you may want to join as a collaborator to the project. Just saying. Yeah, even better. All right, any other question? Well, then let's call it a day. Thank you very much.